In Chapter 8, Part 3, Bond Polarity, we're going to start to think about how two elements share electrons. So before we do that, we need to think about what it means for two elements to share electrons. So do they share them equally? Does one take all of the electrons? What does this mean? So bond polarity is a measure of how well the electrons are shared between two elements. So we can measure that as things that share well or elements that do not share at all. And so classically, bond polarity is divided into two types. We have nonpolar covalent bonds and polar covalent. A nonpolar covalent bond is a bond where the electrons are shared equally. And so that's one type. And then a polar covalent bond is is a bond where the electrons are unequally shared. And so the ability to determine whether a bond is polar covalent or covalent, this is determined. So the bond type is determined based on the electronegativity difference. Between two elements. And so electronegativity is the ability of an atom usually, or in fact always, in a molecule to attract electrons to itself. And so elements with a negative electron affinity and a high ionization energy have a high electronegativity. And so the reality is electronegativity is a scale, and the absolute values for electronegativity can be important. And when you need them for a calculation, I will provide them on a graded assignment. So the values for electronegativity come from electron affinity, ionization energy, and other properties. Such as atomic size. If you were to have combined all of the periodic trends that we've spoken about, these will all be combined together to create electronegativity. So let's think about the periodic trend for electronegativity. If we have our fancy periodic table, and hydrogen here is a 2.1, and fluorine here is a 4.0. So the noble gases are excluded. from our trend. So the trend, as we march across the periodic table, it increases. And as we go down the table, it decreases. So we can tell that a compound created with fluorine would have to have a high electronegativity value, something else. So if we were to think about the polarity of a bond, so bond polarity is determined by the difference in electronegativity. And so some people, myself included, like to use the symbol chi for electronegativity. So we can think about the chi value difference. To classify the differences, let's look at a couple of molecules. So if we look at F2, HF, and lithium fluoride, these are all lithium compounds, and so the values for the electronegativity, F is 4.0, hydrogen is 2.1, and lithium is 1.0. And so when we look at these, we're going to be able to subtract these. So for fluorine, 4.0 minus 4.0, in fact, equals 0. For HF, we have 4.0 minus 2.1, which is 1.9. And for lithium fluoride, we have 4.0 minus 1.0, which gives us 3.0. As we consider the difference between these molecules, these three values are actually going to tell us about the types of bond. So a 0 value is nonpolar. And that makes sense because fluorine is unlikely to be able to hoard the electrons from itself. So when two things are in equal balance, they don't actually have an unbalanced system. For HF, this is a polar covalent bond. In this case, one of these two elements will hoard the electron density in comparison to the other. However, a lithium fluoride bond has a difference of 3, and this is an ionic bond. And in an ionic bond, as we previously learned, the electrons are basically given to one another. So you can think about this if two elements are sharing a blanket. For a nonpolar bond, they share equally. In a polar covalent bond, one element gets more than the other. In an anionic bond, one element takes the electrons. And so it turns out that it's not just 0, 1.9, or 3, but there are ranges for all of these. So let's think about the different ranges that we have. So for a nonpolar bond, I would give you the differential chi values of approximately 0 to 0.4. And so it is perhaps a slight polarity to the bond, but mostly nonpolar. Polar is going to be 0.5 to approximately 2.9, give or take. And then an ionic bond is above 3. And so what you can see is a nonpolar bond has slight sharing. In a polar bond, we see different values of how much or how little the sharing will be. In an ionic bond, it is above 3.0. It's worth noting that we know that an ionic bond is a nonmetal metal complex, whereas both polar and nonpolar are usually created of nonmetal bonds. So let's think about what it means when the electrons are not equally shared. So when electrons are unequally shared, we get these things called a dipole moment. And we've seen these before. These are slight charges on atoms within a neutral molecule. If I were to draw out the electron density for HF in lithium fluoride in these compounds, so we have both elements, and what we would see is that instead of two equal spheres, we would basically see a more and more shift of electrons towards fluorine. And so if we were to consider what do the electrons really look like, on this end we would have a partial positive, and this would be a partial negative. So this delta symbol means partial, and this is negative. And on the other side, it's a partial positive. So this shift of the electron density, where basically the fluorine has more electrons than the hydrogen, gives it a slightly negative charge. Not enough like in an ionic compound where you have a full negative charge or a full positive charge. This is just a little. So the dipole moment is the measurement of how far that goes. And so in this case, if we want to think about HF, we have a dipole moment, and the dipole moment tells us where the distribution of the charge is. And so we draw that with an arrow, where the plus sign is on the delta plus, and the arrowhead is on the negative, or the arrow points to the most electronegative element. So in this case, HF, fluorine is more electronegative than hydrogen, thus it hoards more of the electrons. So let's think about what this means. So given the electronegativity scale, if we want to consider which of the bonds, a boron chlorine, a carbon chlorine, or a phosphorus fluorine, phosphorus chlorine, which of these bonds are the most electronegative? So in this case, or the most polar, we want to be able to think about what that would be. So we would calculate that by subtracting the electronegativity values. So chlorine minus boron would be 3 minus 2, 1.0. Chlorine minus carbon would be 3 minus 2.5, 0.5, slightly polar. Fluorine minus phosphorus would be 4.0 minus 2.1, which would give us 1.9. And phosphorus chlorine bond would give us just 0.9. So we know that the phosphorus chlorine bond is the most polar. And so if we were to draw that, we would draw that by drawing the phosphorus fluorine bond and pointing in this direction. And so the arrow can go on top of the bond or on the bottom, but we do know that this tells us that we have a delta plus on this side and a delta minus on the other side. So we can think about this, and we can actually start to quantify dipole moments. So to calculate the dipole moment, we're going to use this equation where mu equals Q times R. This is a deceptively simple equation where mu is the dipole moment, Q is the charge, and R is the radius, otherwise known as, in this case, the bond length. And so when we think about Q, dipole moments are reported in debye's. And so debye's, so 1 debye is equal to 3.34 times 10 to the negative 30th coulomb meters. So coulomb, this is coulomb, C-O meters, and coulomb is the unit of electron charge. And so this is basically going to allow us to take a very small value and turn it into a number like 1 or a dipole moment of 6 or something along that way. So if we have a fully separated charge, so for an ionic compound, this means we have full charge separation. So we have full charge separation at 1.0 angstrom. So we want to calculate the dipole moment. And so in this case, mu equals QR. So our charge is 1.60 times 10 to the negative 19 coulombs multiplied by our 1.00 angstroms. Now we need to convert because the dipole moment is given in coulomb meter, in debye's, and now we have coulomb angstroms. None of those are the right units. So we want to convert, so there are, in 1 angstrom, there's 1 times 10 to the negative 10 meters. I'll move that over a little. And there is 3.34 times 10 to the negative 30th coulomb meters in 1 debye. So when we plug this into our calculator, we should get 4.79 debye. So you may be wondering where this value right here came from. That is the charge on an electron. And you do not need to memorize that. It should be on an equation sheet that I provide or that you create. So now let's work an example problem. So our example problem states that the bond length of HCl is 1.27 angstroms. In part A, we want to calculate the dipole moment. And in part B, it says if the real dipole is 1.08 angstroms, no, 1.08 debye, what is the partial charge in terms of E minus? So let's look at the first part. So in part A, we know that mu equals QR, so mu is going to equal the charge on the electron, which is 1.60 times 10 to the negative 19 coulombs, multiplied by our 1.27 angstroms, that's our radius. Now we're going to do our conversions of 1 angstrom is 1 times 10 to the negative 10 meters. And there are 3.34 times 10 to the negative 30 coulomb meters in 1 debye. So mu is going to equal 6.08 debye. So this tells us that we don't have an ionic bond where we have full charge separation. We know based on part B that the dipole is really just 1.08. So what is the partial charge in terms of electrons? So in part B, it's a little bit different. So we know we're going to look for charge, which is equal to mu over R. And so in this case, we know that mu is 1.08 debye, and our radius is still 1.27 angstroms. So now that we have this, we need to convert into something else. So we know that it's 1.27 angstroms, so 1 angstrom is 1 times 10 to the negative 10 meters. And in 1 debye, there are 3.34 times 10 to the negative 30th coulomb meters. So when you plug this into your calculator, you actually get that the charge equals 2.84 times 10 to the negative 20th coulombs. However, the question asks for this in terms of E minus. So instead of thinking about this random charge, we really want to know what fraction of an electron is on either side. So we can use the charge on an electron, 1.60 times 10 to the negative 19 coulombs is 1 electron. And that gives us that the charge in terms of electron is 0.178 E minus, meaning we have a slight charge that looks like this. We have negative 0.178 E minus and a positive 0.178 E minus, to where we see a slight charge. Roughly about 17% of an electron charge is negative on the chlorine, and we see the equal and opposite positive charge on the other side. So let's think about how we can think about bond polarity. So we can determine that with bond length, the higher the dipole moment, the shorter the bond. For example, if we look at HF and HCl, the bond length for both of these in angstroms is going to be 0.92 and 1.27. The chi differential is 1.9 and 0.9, but the dipole moment is 1.82 and 1.08. And so what we see is that as they shift, we see slight differences. The other way we can start to think about bond polarity, and so we can think about whether, we can determine what the bond type, so we can identify bond types. As we get further along in this semester or in this course, we're going to be able to determine the polarity of complex systems. So we're going to be able to determine if polar bonds mixed together create polar molecules. And so we can also identify whether this is a ionic or covalent molecule, or if we see ionic or covalent bonds mixed in a molecule with both ionic and covalent bonds.